Okay, so here we're going to take a look at example number 2. We're going to be talking about, can I take a transformation and actually understand the regions that it begins to manipulate and how it manipulates these regions? Okay, so an important thing to recall at this point again is that this transformation of t is taking in u and v values, and what it's spitting out again is an x comma y value. So this transformation is taking a region in the UV plane and it is transforming it into something in the XY plane. This is the goal. Take something over here and transform it into something over here. So we want to see how this actually works and what these kind of different blue regions might look like. So here's the idea. I'm going to take this transformation right now, and my goal here is to find the image of the following square that exists in the UV plane. Okay, so I'm actually going to erase these pictures that I have here and maybe try to update them with some new pictures. I'm going to take this square, which is going to exist in my right picture, and I'm going to be curious, what does t transform it into? And my hint here is to determine what does t ultimately do to the boundaries of that region. Okay, so let's see how this would actually work. I'm going to go ahead and start by taking a look at least my region in the UV plane. It seems here, like in the UV plane, my region S is all points u comma v, where u goes from 0 to 1, and v goes from 0 to 1. So I have this nice little square-shaped region. Okay, so this right here, this is S. All right, and t is going to take that region, it's going to mold it, like some clay or something like that, into a different shaped region. And I'm curious how that t is going to do it. Again, I can imagine moving around different points. Like if I was to take the point 0, 0, and I would plug it in for u and v, I can see where that's going to get mapped to in the new red region of D. That's going to get mapped to the point, well, let's see, if u and v are both zeros, I'm going to get 0, 0. So this point is actually going to not really move at all by the transformation. But I can see where the point 1, 1 is going to go over here in this region. My point 1, 1 is going to turn into, what is that going to be, 0, 2. So I can see some of these points are going to start to move around, but I don't know exactly how they're all going to move. But let's take a look at each of the edges to get a sense of how this would actually work. All right, so I'll start by saying here that we will analyze all 4 boundaries of S. Okay, so I'm going to start by labeling each one of these sides in my picture. Notice that this bottom side over here in my square is given by the formula v is a 0. The top side then is given where v is a 1. My right side and left side are given by u equals a 0 and u equals a 1. So it doesn't matter which one of these I start with. For the sake of argument, let's start with the very left side. Okay, so we'll go ahead and take a look at this. We'll say for u equal to 0, where notice we kind of have some bounds on the value of v. When u is equal to 0, v ranges from 0 to 1. We have, and we can kind of see how this gets transformed. So let's see. We would know that when I take a look at my transformation of u comma v, in this case, if u is always 0, then I can kind of put in a 0 here. And if that's the case, I can see what the formula for the x comma y's is going to be equal to. I'm going to get negative v squared comma 0 for the transformation. So what I'll notice here is that this kind of implies that x is going to be equal to a negative v squared and y is going to be equal to 0. Right? This is what I end up with for this transformation. So I can say that if I was to take a look at this, we have that y is going to be equal to 0 all the time here. And if x is always going to be equal to a negative v squared, and v is a number that goes from -1 to, sorry, from 0 to 1, then x is going to be a value that also takes on a specific range. Notice if v is a 0, x would be a 0. If v is a 1, x is a -1. So I can go ahead and claim this. Now I'm going to go ahead over here on the side, and I'm going to start to draw out what my picture of my XY plane is going to look like. Now I'm going to give away a little bit of information here in the way that I'm drawing this picture. You'll see that I am producing a little bit of a negative x-axis, but we'll see kind of where this comes from in just a moment. I'm going to go ahead right now and try to draw this side of the region over here, and I'm going to see how it gets transformed. So again, I'm taking that side of u equals 0, and it looks like I can turn it into the following. It's the side where y is 0 and x goes from -1 to 1. So that left side of the picture up there has kind of been morphed into this right here. Okay, so this is great. We've done one of the sides. We just need to do 3 more. So why don't we go ahead and let's do the right side. Let's do when u is equal to 1. That way things are pretty similar. When u is equal to 1, again, we still have v going from 0 to 1 on that side, right? Because the lowest v is 0, it goes up to 1. For that, again, we have, well, this time, in place of u, I can always put in a 1. And now when I think about what the formula actually produces, if u is always a 1, then I'm going to get 1 minus a v squared, or sorry, a y squared, excuse me, 1 minus a y squared, and then I'm going to get a 2v. So this is the formula ultimately that I'm going to be constructing here. All right, so let's see. This tells me that x is equal to 1 minus a y squared, and I know that y here is equal to 2v. So again, I can see that one of these formulas has no u's and v's in it at all, and another one does. So I can see over here then I have one side that can kind of be graphed out as a nice red side of a picture for my region down here. But I can also see that y, since it depends on v, is going to be bounded between some values. If y is always double the size of v, and v goes from 0 to 1, then clearly y would have to go from 0 to 2. So I'm going to go ahead and quickly note on my y-axis here, let's say this is the value of 2. That's the highest y can get. And so what I'm going to see is from 0 to 2, on my y-axis, I'm going to have to go ahead and actually construct and build this picture. So I'm curious, what does x equals 1 minus y squared look like? Well, that's not actually too surprising. That should, oh, wait a minute. I think I made a small mistake here. Maybe you already caught it. I think this underlined red line here is really throwing me off. When I went ahead and I actually replaced this values of 1 and v in here, this should be, excuse me, 1 minus a v squared. That definitely changes some things up here. Okay, so if I have this as a 1 minus a v squared, then I have to go ahead and make a couple modifications. I'll go ahead and make a simple modification for this. I can actually change that v back into something with a y by recognizing that v, based on my second formula here, is the same as a y over 2 all squared. Okay, so I'll still have some sort of a sideways parabola type picture that I can go ahead and draw here. I'll notice that this is a parabola that opens towards negative x's and starts at the value of 1. Okay, so I'll notice here also that when I plug in the value of 2 for y, I get back a 1 that gets squared, and then I get x coordinate 0. So I'm going to get a sideways parabola that looks something like the following. Now you could probably imagine what the rest of this parabola is actually going to look like. It would also exist kind of moving out down here, but for the moment I'm not going to need that portion of it. I'll leave that in the picture just for the moment so we can see why I won't consider that portion. Okay, we have 2 more sides to map over, so let's start by taking a look at when v is equal to 0. When v is equal to 0, we see there that u is going to be a value that runs from 0 to 1. And so I can think about what happens in the transformation. Here, I'm going to have u and 0 in place of v. So that means I'm going to end up with a u squared and ultimately a 0. When I think about what this gives me, this tells me that x is the same as a u squared and y is the same as a 0. Well, again, this is great because I have something automatically in y equals 0 that's some sort of a red line I can sketch. And I can see again that x, if it's the same as u squared, and u ranges from 0 to 1, x is definitely going to range from 0 to 1 as well. So if I graph this in the picture, what I can see is that this v equals 0 side is going to get shifted and transformed into, well, it looks like this side right here. You can start to see now why I might not need this bottom portion of this parabola that we sketched up above, because it doesn't seem like it's closing in any sort of a region. Again, we'll leave it for the moment and erase it once we confirm that it's not necessary. The last side I have to transform is when v is equal to 1. So again, here I'm going to have u's ranging from 0 to 1. I'm going to have u comma 1. That, of course, is going to come out equal to a u squared minus a 1. And I'm going to have a 2u. So, of course, that gives me x is equal to a u squared minus a 1, and y is equal to a 2u. I don't have any formula here that is completely not containing u's and v's, but I can certainly get one. I can go ahead and actually replace the u over here with a y over 2. So I'll write this as x is equal to y over 2 squared minus 1. And I can see that, again, if u goes from 0 to 1 and y is double the size all the time, y is going to go from 0 to 2. What I'll notice here is this is a parabola that starts at x is negative 1, and it opens in the positive direction of x's. It's going to be a parabola that looks something like this. And again, I could imagine the region down here. So if I'm going to go ahead and think about transforming this, I can start to see here that I've been able to construct a region in the xy plane that corresponds to the blue region I had up here. So this region is my region of D. And I can see how I kind of have these 4 sides here creating these other 4 sides over here. So this is the idea of how I actually construct one of these deal with one of these transformations. Again, I can see that the transformation T is supposed to take in u's and v's and spit out a red region with x's and y's. In the next video, we'll take a look at another example of this, of how we can practice doing these sorts of conversions.